Okay, so the crack the whip skating, I actually made it look like a person being pulled by a rope, but basically it's a whole bunch of people in a line. And the person on the end is going the fastest because they have to travel the greater circumference. So they, therefore, they have the biggest, they need the biggest centripetal force. And so they're most likely to fly off tangent. So the first thing I want you to do is to imagine the plane. That's kind of hard to see that yellow. Imagine the plane of the circle that the person is going in. So they are traveling in a circle of radius 6.1 meters. From a bird's eye view, again, this is really like a whole line of people playing crack the whip. And this person is flying off, trying to fly off tangent. And then they're locking arms, and that's what's holding them in. Okay, so my questions will always ask you to draw a force diagram because that's what's needed, and I hate that the book doesn't ask you to do that. So you're going to continue to use your we must never forget this. And the person has a weight. There's no mechanical forces. They are touching the ice. That's a surface. So there is a normal force. The reason they put them on ice is so that there's no friction. And I'm going to call this tension. You know, it's not really a rope, but it's like they're locking arms or elbows with the person. So it's really, anyway, I hope you feel like, okay, it's like tension. So it's kind of like whipping the tennis ball around in the gym, which we did in 2025. Hopefully you did that before you did this problem set, because that'll help understand it. Okay, so instead of doing horizontal and vertical, we are going to do radial and non-radial. Non-radially, that means perpendicular to this plane of the circle. The normal and the weight are balanced. It's a boring problem. The normal equals the weight. Okay, that's not really important. I'm just trying to show you that we do think about every force on the force diagram and the difference between radial and non-radial, but we're not going to need that. Radially, the sum of the forces equals mv squared over r. And remember, the goofy mnemonic is in must win. So the tension is pointing towards the center of the circle. So that is positive. It is pointing in. There are no forces pointing radially outward. So again, you can win by default. So the tension that person needs to have in their hand or locking their elbows is equal to their mass times their velocity squared over the radius. So I think we're ready to just plug in the numbers that were given. The person's mass is 80 kilograms. Their speed is 6.8 meters per second squared, and the radius is 6.1 meters. Looking at my physical key, it might have said find the centripetal acceleration. I'm not sure. But this is what I care about, is that person, kind of like tug of war, in order for them not to, lose contact with the rope, they have got to exert, they got to be able to hold on with 606 newtons, and people weigh about 650 to 700 newtons. So that's not easy necessarily. Okay, that is question 1. Okay, so this one is super similar to flinging that tennis ball around in the gym. So you need to know the inertia of the ball, because the more inertia it has, the more it wants to fly off tangent, the more tension you're going to need. You clearly need the radius. That's in v squared over r. And you have information about time, which is going to give you indirectly information about how fast it is moving. Technically, there is, when we do the Flying Pig Lab, technically there is weight, and we're going to see the flying pig has to kind of move at an angle so that, just like with the Coulomb's law lab we did, that part of the tension is balancing the weight. Okay, we are ignoring that. We are assuming that that angle is basically zero, otherwise we have to do vector breakdown. So this is a little bit of a fake problem in that we are assuming that this tension is purely horizontal, which means it's in the plane of the circle, which means it's in the radial column. So what that means is that the non-radial column is kind of bogus because we don't really have anything balancing the weight. Okay, so don't love that. But question A says, find the tension. The tension is what's pulling the object inward, so tension equals mv squared over r. That is in our radial column. And hopefully that makes sense. The tension is the only force pulling it in. We got the mass, we got the radius, but we don't have the speed. So we're going to do like a sidebar column, and the speed is 1 circumference over the time to do 1 circumference. And if you feel like you want more practice with this concept, then go back and do the first problem set. So we have 2 pi times 0.10 meters. That's how far it travels once around, and it does that every half a second. So that gives us a speed of 1.26 meters per second. And now we're ready to plug and chug into 0.012 kilograms times the velocity squared over the radius, which is 0.10. So the tension is 0.191 newtons. Not very big because it's a pretty light ball, so it doesn't have a lot of inertia. Okay, question B says, what happens if you double the speed? So if you double the speed, then V is going to be 2 times 1.26. Or 2.52 meters per second. Okay, so the tennis ball is going twice as fast. So you might assume the tension's going to double. But the trick is that the velocity is squared. Okay, so I'm going to do out the math for you, but if you plug that in, because you are squaring what happened to the velocity, you get 0.762 newtons. And so if you do a lot of physics or math or economics or all that kind of stuff, you will see that logically, if I double the speed and then square it, 2 squared is 4. So the tension is 4 times bigger. But if you are still practicing that skill, you can just do out the numbers and say my tension is 7.62. It was 0.191. And then if you divide those two, I'm double checking because I don't know how much rounding there was, you get 3.99, which is basically 4 times bigger. Okay, so you don't have to do the math out. You can logic that through to say, if I double the speed and then I square what I double, I get a factor of 4. Okay, that's why when you're driving your car, you want to be careful because you want to think about, if I double my speed, we don't know this yet, but the kinetic energy is also velocity squared, and you're going in your energy is 4 times as much. Okay, so you just want to be careful with how all of the variables are related. Okay, so this is the last question, and this will help us start thinking about the video lab we're going to do later on this week. So you're in an amusement park, and there is a cylindrically shaped chamber, and they're sitting on chairs. At one instance, the outer wall moves at a speed of 3.2 meters per second. That's a little bit confusing, I think, but what that means is the person, bird's eye view, person is sitting here, that wall, if you had a speedometer on that wall is moving 3.2. So what that means is that wall is covering ground going in a circle at 3.2 meters per second. Okay, and we know the inertia, the mass of the person, and we're given that they feel this 560 Newton force. That is another word for the normal force is 560 Newtons. And then they want to know, hey, what's the radius of this chamber? Okay, so again, visualize that the circle that the person is going in, you can see that that normal force is pointing towards the center of the circle. So in our radial column, you always have the sum of the forces equals mv squared over r. And the only force pushing that person in, like the racquetball and the hula hoop, is the normal force. So they also have weight, and they're sitting in a chair so that there is a normal from the seat. So there's actually two normals. So I don't know if we want to call that N sub S for normal seat and N sub W for normal wall. So in the non-radial column, it's a boring problem. The normal force on their seat equals their weight. And radially, we know that they're feeling 560 newtons of pressure against the wall. It's pointing in, and in must win, in is positive. That's what's pushing them in. They're trying to fly off tangent, and they're literally running into the wall, and the wall pushes them back. Remember, the wall is a reactive force. And then they run into the wall this way, and the wall pushes them back. And then they run into the wall this way, and the wall pushes them back. Like the animation from the first day that we talked about circular motion, and if you were absent that day, go back to the slide deck and watch that animation of I think it was a pink ball bouncing inside a hula hoop. Okay, so sorry, getting distracted. The mass is 83 kilograms. The speed is 3.2 meters per second, and we are looking for the radius. So I'm going to pause because I did this a different way. Okay, so I cross multiplied 560R equals, this works out to 850, and then divide both sides by 560, and you get the radius equals 1.52 meters. All right, so the whole point of this problem set was to practice in the radial column saying the inward forces equals mv squared over r, and connecting that back to the forces that we've already talked about this year. Hope that went well for you, and I will see you in class.